Siddhi, proceed.
Good evening, everyone. Welcome to the Centenary Celebration of Department of Mechanical Engineering, IIEST Shibpur. I am Siddhi Suman, a third year undergraduate student of this institute and host for this evening. Today, we all are here for the 41st lecture under the Centenary Lecture series, which is to be delivered by our honorable guest, Dr. Pradip Saha, on the topic Overview of Global Aerospace Parts Manufacturing Technologies. This session will be chaired by Professor Subhash Chandra Mondal, who is professor in the Department of Mechanical Engineering at IIEST Shibpur. I would like to invite Professor Subhash Chandra Mondal sir for the further continuation of the program. Sir.
Professor Mondal, please. Please unmute.
Good evening, all of you. I welcome Dr. Pradip Saha to deliver to his credit. He is the author of a couple of books, for example, Aluminum Extrusion Technology, published in ASM International in 2000, and Aerospace Manufacturing Processes, published by CRC Press in 2017. He has also authored a couple of book chapters for ASM handbooks. He has published 26 research papers in extrusion and metal forming technology in national and international proceedings and journals. In this talk, Dr. Saha will talk about manufacturing processes for aircraft component, including activities consisting of multiple materials processing technologies. He will focus mainly on the major aerospace materials and manufacturing process technology. This talk will also provide first-hand industry insight about aerospace manufacturing to the students seeking an introduction to the aerospace industry. This is very much interesting area, and he is our alumni of 1974 batch. Now I will invite Dr. Saha to deliver his speech. Dr. Saha, please.
Yeah. Oh, thank you so much for the nice introduction. So before I start presenting my paper, my talk today, I will acknowledge some few persons that our Gautam Sengupta is our family friends in Seattle. He has first mentioned to me that Pradeep, there is some mechanical engineering lecture session is going on, and I got the invitation, and I'm going to introduce your name to I think Professor Shudeep Shudeep Ghosh, I believe, yes, and I must thank you to Gautam Sengupta or Gautam Da for giving me that introduction to that Shibpur B College. I'm still calling Shibpur B College, you know, to the mechanical engineering department, and also I must thank you to the committee to accept my offer to give a lecture today to the excellent audience, including the students, and and also before I start talking, a couple of more things I must mention about my experience and my personal lifestyle in Shibpur B College, and that whatever I learned from there, I'm still using the same fundamentals that I learned many years ago, and I must salute my college, and and we got the very strong foundation from B College. I can never forget in my life, and this opportunity is giving me and reminding me a lot of my old memories and bringing my personal feelings in front of you, that how much happy I am today to give lectures to the current students of that Shibpur B College, So, okay. So let me start talking about that my topics. I'm in the aerospace for the last 25 years in the Boeing company, and I started from the very beginning as a research engineer. Then I moved to in the Boeing fellowship program gradually through the through my activities and my research work that I have provided to the company for the future advancements. So, so basically, what I'm going to cover today, I'm going to cover a very short one. Going to show you a very short video of various aerospace vehicles that Boeing has developed, and there are a lot of things, but still, I'm going to show you a short video that was available in our Boeing site. Then I'll be talking about the current aviation market outlook, then overview of major components of an aircraft, major aircraft materials and its classifications, major manufacturing technology, that the main topics, then measurements and inspection methods in manufacturing. I'll talk about fundamentals of some research and development, then how the automation and innovation is coming to the manufacturing gradually, then what are the future needs for manufacturing, some show you some future aviation, and then conclude with the summary. So let me show you that video. You may not hear the sound, but I can, you can see that actually sound is basically music, but you can see that different aerospace vehicles. Okay, so the video shows that the Boeing has all sorts of activities, including the Boeing commercials to the Boeing military, but to Boeing space, and luckily I had an opportunity to work for all various programs that I involved, and I had a lot of contributions to even the space satellite that your CLS program that I worked on few years ago on this particular project. So here is the forecast for that 20 years from 2014 to 2034. You know how that world economy is affecting the strong long-term growth. The number of airlines passengers like 4%, world economy is 3.1%, and airline traffic RPK is a revenue per kilometer and RTK is a revenue ton kilometer for the cargo traffic. So basically the commercial aircrafts are built for both your passengers carrying and and that your cargo carrying capacities. So what's the market trends looks like? The market trends basically is driven by the growth by emerging economies. You know, the current economy is not that strong, and because of that, you have seen that one how the airlines industry is affected before it during the pandemic time is now gradually slowly recovering from that one. So it is also the market much more diverse and balanced market, you know, all over the world, like a different country has a different requirements uh, and based on their own country's passengers demands. And there is also continued to the strong replacements when the aircrafts are becoming too old. It's the time to replace the aircraft, you know, and then that the new airplanes capabilities, you know, say for an example, our 787 dash 8, 9, and 10, and the new airplane is coming that is called 777 dash 8, 9 is coming maybe in 2024 that all the passengers will be flying. So this plane is under testing at this moment. So how that change of fleet compositions in the next 20 years, as you could see from the pie chart from left to right, the regional jet is changing from 11 to 13%. Single aisle aircraft means, as an example of 737 is the most popular, and that is moving from 65 to 70%. The small wide body is the 767 and also 787 has some. 787-8 is a small wide body that is moving from 11 to 13%, and your medium wide body is moving from 8 to 9%, and the large aircraft, the very large aircraft like your Airbus A380 or our 747 is moving from 3 to 2%. So that's that your next 20 years trend has been forecast. So what drives the innovation in aerospace? So basically that I highlighted some of the bullets over here is the traffic forecast, network development, economic growth, market liberalization, airplane capabilities. Fuel price is very much affecting that your economy of the airlines and their profitability. Infrastructure, environment is a very important. Then transportations and the airline strategies and the different business model of the different airlines customers. So This particular slide that I'm trying to show you is beyond the first century of aerospace manufacturing. As you could see from the left-hand side, that initially when that the flying vehicles has started developing, you can see that how that cotton fabrics are being used to make that airplane wing. As you could see that all the women, they are doing that using the cotton fabrics and developing that wing skin, the wing structure. And the bottom of that one, you can see that how the automation is coming as a composite layout fabrications for, so for an example, like an wing skin, as you could see. Then the middle column, as you could see from conventional machining in the top of that one, is coming to the additive manufacturing. Like instead of losing the material, you are adding the material as an additive manufacturing to make an integrated part by depositing the metals. And the right hand side, as you could see, your uh, your how that automation, like a regular fasteners and other things, they are putting it manually to the automations by the robotic technology. So what are the market challenges and what are the customers need? So basically, the market challenges that it has to be a very safe, so that the people can safely fly in the aircraft. It could be affordable, very reliable from point to point, hub to hub, that there'll be no problem, no issues. You can upgrade the aircraft. You can have a flexibility of using uh, of the aircraft. Then how the aircraft is that the performance based, how that it is environmentally responsible. So for that, as you all know, that the people all over the world is thinking about how the environment will be looking like, for the so that's why we are doing a lot of work, that how that the different fuel compositions can reduce the emissions in the whole world actually. And the availability of the aircraft that you are looking for, you have that if they have I'm sorry, that you have the aircraft available for the users. So that's why the continuous development of aircraft development is going on. So what are the technology and investment on future needs? So we are looking for the extreme affordability, breakthrough performance, enduring sustainability, and environmentally responsible. So that's the main focusing technology investments for the future. So now I'm moving to the actual topics of overview of major components of an aircraft before I start talking on the manufacturing of the parts. So basically, as you can see in the top, this is a 777 aircraft, and as in the bottom figure, you can see a schematic representation of the structural and operating system components. There are multiple components, as you could see on this sketch. In starting from the fuselage to the wing, to the vertical stabilizers, the engine components and the landing gears. So in this diagram, I'm going to show you that what are the major components, structural components looks like. Those are all external shapes, like your fuselage, the body, the wing, and the stabilizers. And there are some under that undercarriage, there is a keel beam and the landing gear. Those are internally installed inside that aircraft. And on the wing, there's a engine and nacelle and pylon. And so those are the major components like your fuselage, wing, and stabilizer. So now I'm moving to that structural part of the fuselage section. As you could see, there's a on the figure C, there's an example of a upper lobe of a section of a fuselage. So fuselage has three major components, like your skin, that's the skin, that's the stringers, goes along that length of the aircraft. The frame is a transverse component. As you could see, those are the frames. And what are the input metal to manufacture those? The skin is made out of the sheet or plate products. Either is a bare aluminum or a clad. And that stringers is made out of sheet as well as extruded product. The frame is made out of also that the sheet product, like a is plain sheet, then you formed into the shape and then you make the frame out of it. Then also could be an extrusion product. So the major structural components for the wing has a very similar things. It has a skin panels. As you could see, the upper part of the wing when you were flying in the aircraft, that is called the skin. Then the spars, those are the spar is called the front spar. In the back there is a rear spar. Let me see if I could minimize that one. So that's the rear spar and the front spar. And the stringers are going along the length of the wing. There is this called the rib. You know, like our human body, we have the rib on our chest case. And then the input materials are the skins are made out of plate, spars are made out of plate and extrusions, stringers are made out of extrusions, and rib are made out of sheet and extrusions. So those are the basic components of various aircrafts and various aircraft part component as well as the raw material are used to make those components. Okay, so here's this slide is showing you a wing skin assembly. You know, as you could see that the top view is that is the major components. The leading edge of this is called the slats, and this is called the leading edge. This is the trailing edge, and this is the main structural part of the wing is sitting in the middle of that one. And so there it has a fixed trailing edge and a movable trailing edge. And the bottom photographs is showing you the actual the wing that will be attached to the fuselage later for a 777 aircraft. So ready to join. So now I'm going to show you the stabilizer part, the back of the aircraft. Basically has the very similar concept and the structural components. It has a two left and right spars, vertical stabilizers, and the rudder components. Then let's talk about the major components of the landing gear. So as you could see on the right hand side, there's the schematic diagrams of showing the landing gears. The landing gear has a lot of very strong structural components to carry out the entire gross loads and the dynamic load when it is landing and takeoff. So it has a components called strut, link, brace, truck beam, and trunnion. And most of the components are made out of the input raw material called forging. Those are very high strength material. Most of the materials are titanium and steel, and there are few components are also aluminum forged also. Here is a schematic view of showing that engine and cowling components. The top one is that the schematic diagram. The bottom one has some cowling components showing you, and basically, it has a nacelles in the front. We call the lip skin, where the air is going inside through that, and then finally going to that exhaust gas of the engine is going to the exhaust systems from the back of the engine. Now I'm moving to major aircraft materials and its classifications. So there are various materials are being used to make various aircraft components. So on the left-hand column is a metal structure. The primary metals are, it could be a non-ferrous and ferrous. And input, so for ferrous and non-ferrous, the input raw materials, you are making it by melting process and alloy making. Then you are casting the ingots and billets, and then going through the fabrication process by rolling, extrusion, forging, and many more processes to make that your structural material. So that non-structural side, the metals, non-metal side is a composite material. It is the major components are polymer matrix, metal matrix, and the ceramic matrix. What are the input raw materials to make those? There are fibers or fabrics, matrices, prepreg tow or tape or fabrics. What are the fabrication processes? Normally autoclave, vacuum bag molding, compression molding, and many more other processes are being used. So this slide is showing you the application of different materials in a commercial aircraft. As you could see on the left hand side, on the alloy sides, there are titanium material, there are aluminum material 2000 series, 7000 series. There are a lot of titanium alloys, 6-4 titanium. There are composite material, carbon fiber, reinforcement plastic composites. So as you could see, different color coded are showing on this diagram is showing you a different materials or where the different materials are going in different areas of the aircraft. So this pie chart is showing you how that composite is growing from a 747 model to the 787 model. When the 747 came in, we have composite of only 1%, and 81% is mainly aluminum. Then moving to the 767, that composite has grown from 1 to 3%. Then when that we developed the 777 in the 1990s time frame, then you can see the composite grown to 11%. Then when in 787 came in 2011, the composite was 50%, like a half a composite material into the aircraft. Here is that 787 components are how you can see that there are carbon laminate, carbon sandwich, other composites, aluminum, very few areas. Major titanium, because the titanium is a compatible material with the composites because due to the galvanic reactions with the aluminum to the composites, aluminum is not much used, and whenever the aluminum is being used, there is an interface between the aluminum and the composites. There is some titanium foils or titanium sheets are attached to that one. So here is some example of the pie chart example of how for the military aircraft, like an FA-18, the composite was 10%. FA-18E and F was composite was 19%. F-22, 42, I'm sorry, composite was 24%. Since the composite is growing, the titanium is growing as because the titanium is comparable to the composite material. And then when F-35 came in, you can see the composite was 40% increased. So now I'm moving to show you the uses of different materials, the wrought product we call, that sheet or plate, extrusions, forging, how much of the percentage are being used in the aircraft. As you could see on this top pie chart, that 48% of the total material is used is a sheet and plate product, and 24% is an extruded product, 15% forging, and 13% some other materials. And those are the at the bottom figures, those are the fundamentals of rolling and sheet production process, extrusion, and the forging process. Now I'm moving to that major manufacturing technology for the aerospace. That's the main topics of my lecture today. So this chart is showing you the fundamentals of manufacturing aerospace parts. So when that design from the design part design is coming out, then is the aerospace part description is coming, then detailed design and drawing preparation, then the selection of the aerospace materials, it's a metal or non-metal, and when you are selecting the metals and non-metals materials, there are a lot of research and development is coming in for the selection of material. There are a lot of material specifications are coming into when the material is selected, the specifications are being made. There are, when you are making the material, you need to make sure that the material is a manufacturable material. Some of the materials are being used, but you cannot make the part suitable manufacturing process to use it to make the part properly, to qualify the part to use in the aircraft. So then it's coming to the manufacturing cost and quality, and final, the inspections and acceptance of the part to the aircraft. So there are all those blocks I'm showing you on this flow diagram is the major activities that we need to consider to manufacture the aerospace parts. So now I'm going to the manufacturing technology side. So what are the different manufacturing technologies that are coming to manufacture ferrous and non-ferrous metals? There are forming technologies, welding technologies, metal cutting and machining technologies, abrasive metal removal and cutting processes, chemical metal and chemical processing of the metals. There are a lot of activities you need to do to make the part from forming to the final finishing of the metals. So I'm going to show you just one quick slide on this one, that how that the tribology is one of my research field. My PhD work was on tribology, means friction, wear, and lubrication process. Tribology is the major three components of the is the rubbing between the two metals, two surfaces. So it deals with the surface topography, it deals with the friction and lubrication process between tool and the workpiece, and during the your friction process and sliding process, the metals are going into some wear process by abrasive wear or adhesive wear, and how that role of tribology is affecting our different processes. Like your metal forming process is a friction control process. Welding and technology, some of that welding technology are friction star welding or linear friction welding. Then is in moving, there is a frictional, when you are doing the machining process, there are frictional heat control process, and abrasive metal and metal removal process is your lot of things are done by the abrasive process, your abrasive materials, abrasive wheels that you are using to remove the materials. So under the forming technology of various metals, there are different forming technologies. So on the left hand side, this figure is forming technology for the sheet metal products. The sheet metal products forming technologies are is called the break forming, the bump forming, roll bending, stretch forming, hydropress forming, roll forming, juggle forming, deep draw hydro forming, mass die forming, spin forming. I think, I'm not sure these days, when I was my master's program in Shibpur B College, Professor Ranjit Ghosh was my professor to teach that metal forming classes, and that is one of the most interested area, and I learned from B College, and I'm still using it in the Boeing company. I'm basically a forming technology guy in the company, helping the company to move forward in the forming technology. So now I'm moving to that cold forming of the plate product. Plate product has also a bump forming technology is being used, short pin forming technology by, I'll talk about that one a little bit. And the laser shock peening technology is also being used to form the metal. Then the extrusion side, there are stretch forming technologies, forming, roll contouring, and juggle forming. For any forming options, there are three fundamental things, like you are dealing with the current alloy, you are developing a new alloy, then you are testing it, that how the metal is formable, you are doing some formability test before you go for the actual forming technology that are using different machines in the shop floor environment. So here's an example I'm showing you. To the left is a schematic diagram showing you what the bump forming technology is. It's basically a 3-point bend. You can see the punch in the bottom. The die in the bottom and the punch in the top. Punch is pushing the metal and bending with that 3-point bend technology and moving forward. So the same thing the schematic is showing on these photographs it's called that incrementally moving forward between the punch and die, and you can see that there is a graduation that has done. Every step he's moving to the one step, and forming it. And after you finish all those bumps, that material is curved and coming to the curvature of the skin panel of the fuselage sections. Here's an example on the figure C is a bump forming of a windscreen technology. You can see that 1, 2, and 3, there are the 3 point location of giving you that the bending operations. Now is moving to the stage forming. The left-hand figure is showing a schematic representation of fundamentals, what the stage forming looks like. Basically, there is a forming block, there is a flat sheet is stretching by a uniform tension by the hydraulic cylinder from left to right, and the forming block can move up and down, and moving it up and is bending the sheet and then stretching it further beyond the yield point in the plastic deformation stage. And so, and that's the fundamental of the stretch forming. That's one of the machine is showing you on the right hand side in the figure V. That's the machine is used for wing leading edge skin forming. That you can see that part is formed after the stretch forming operations is done over here. This machine on the top I'm showing you, this is the one of the world largest stretch forming machine for stretch forming a very heavy extrusions. So that is a 3,000 ton stretch forming press. As you could see, the forming operations is done in this machine. That's the stretch forming block, means where that extrusion is being stretched to get the contour of the stretch form block, because every part has its own geometry and the precision tolerances to be maintained by the process. So that's why the stretch form block has to be very accurate to do that one. So jaws, the extrusion is clamped in between that two clamping jaws, and it is stretched, and the forming block is moving up to give you the permanent deformations of that your extrusions at the end of the forming. Here's an example of a very heavy extrusions. We call that one is a double plus. You can see two plus sign. That's why we call the double plus card. Is a, one of the largest heavy extrusions is being made by a couple of companies, heavy extrusions, and that is being used into that interface between the wing and the fuselage body. That's the connecting between the wing and the fuselage. So this extrusion will be going for further machining to make to the final geometry of the part actually. So now I'm moving to that. We talked about so far that the forming in that ambient temperature, the room temperature, we call the cold forming. Now I'm moving to the hot forming process. There are few hot forming technologies are being used. Is a superplastic forming, a hot die forming, hot brick forming, and hot stretch forming. There is another under the superplastic forming. There is another forming is called the diffusion bonding. The parts are being diffusion bonded together, and then superplastic form that sandwich diffusion bonded part. And there is also another forming is called the creep edge forming. The material is brought into the aging temperature, and under that aging temperature there is some pressure applied to that one, either by the vacuum bag or by applied by the load, external load, and that under the aging temperature the material is being formed or straightened. Here is a schematic representation I'm showing you that superplastic forming is basically the metal workpiece is placed between the upper and the lower die. The arc and is the material is brought into the plastic forming temperature by increasing the temperature of the material, and then the argon gas is applied into the cavity under pressure, and the pressure is being applied at the temperature is being changed, and then gradually under pressure the material is completely in the superplastic form stage and forming into the shape of the I'm sorry, that from from this shape to this shape, and finally form to the final cavity of the die block. Here are a couple of presses I'm showing you. In a figure A is called the up and down acting press. Figure B is showing is a lower platen shuttle type of press. Is an example of a superplastic foam part. Superplastic temperature is typically 1650 degrees Fahrenheit for a titanium. And hot size, the stress, because after the forming that you need to have a stress relieving operations to remove all the internal stresses developed, that the stress relieving temperature is typically 1350 degrees Fahrenheit. Here are a few examples of superplastic foam parts, 6,4 titanium sheet metal parts. Yeah, as I mentioned about the diffusion bonded, that's the sandwich part, and after that is superplastically formed. Those parts are being used for the heat shield at the back of the engine, as you could see over here. As I mentioned, that hot die forming is also another hot forming operation. That's a pretty heavy top and the bottom top and bottom die. There's an example of the hot die forming process. This is also a part of the heat shield components, as you could see over here. I think it's for 757, very old aircraft. Typical hot forming temperature for titanium is 730 degrees centigrade, 1346 degrees Fahrenheit. So that's a hot forming of a very heavy, thick plate. As you could see on this example is very hard to form if you don't use that hot forming process. It's a titanium and using a ceramic die, very low expensive die. You have, so since you are making not many plate form, this plate is formed for one of the military applications, and not many parts are being produced. So ceramic die would be a less expensive process to do that one. Uh, There's a stitch forming. I mentioned about the stitch forming. That's an example of a titanium extrusion or being stitch formed by using this press. After forming, as you could see, forming along that curvature of that stretch from block, and as you could see, the parts are all titanium extrusion stretch form. So those titanium stretch form parts are used for our 787 aircraft. As I mentioned about that, the titanium is a compatible to the composites. As I've shown you on the cold forming side, the double plus cord, the extrusions are for a aluminum aircraft. Those are aluminum to aluminum, no problem. So now moving to another technology called high energy forming and joining. There are two kinds of um, high energy forming. One is called the explosive forming. These days we change the name to high energy hydroforming. And there is another technology called electromagnetic forming. So this is a schematic diagram showing you the explosive forming. There's a die, and this is your blank. This is put in a vacuum bag, and put it into the water tank. The explosive on the top. That's the distance between. That's called the stand-up distance between the explosive to that top of that metal surface of the. Then that explosive is ignited, and when it is ignited, the explosive is energizing the hydraulics, means the water, and the high energy hydraulic fluid is pushing the metal and it is a very high standard deformation process, and it forms very fast and quickly to the curvature of the die and the contour of the die. Few examples showing you. One of the example is a stainless steel product. That's an aluminum plate product, as you have seen on the previous superplastic form. That's a titanium. That's the aluminum plate product by using the explosive forming technology. Titanium forming an explosive will be rather difficult because of the formability issues of the material. So let me talk about electromagnetic forming. This is one of my very favorite technology that I learned, I applied, and I have done a lot of innovations in this technology for many aircrafts. This is an example I'm showing you as a where the torque tubes are being used. The torque tubes are being used to drive the leading edge of the wing slat and the trailing edge of the wing flaps. When the airplane is taking off, you are extending the flap, and also when it's landing, you are extending further out of the flap, and the leading you are also changing the angle of the leading edge. So how you can do that one? You need to use some torsional tube to drive the flaps. And when you made the torsional tubes, those are made joining a a hollow tube, seamless tube to that. I think I have the slides in the end. No, not that. Okay. So those are the extruded drawn tube, aluminum 2024, and attached to the end fitting at the end like this, and that is formed by electromagnetic forming by, you can see this is a schematic diagram, the electromagnetic forming. So basically you have that magnetic coil, you have the workpiece in between, and when you are discharging the current, the eddy current is induced over here, and because of that eddy current, your two different directions of the forces are coming in, there's a huge amount of compressive forces coming in to collapse the tube into the end fitting to form the part. Excuse me. So now I'm moving to, there are a lot of tube and duct applications in the aircraft, mostly for the air circulations processes, and also some of the tie rods and the switch ports. So, so what are the applications? What are the forming technology are being used? There are bending process, there are forming process, there are swaging process, there are some of the transition in forming processes. Under bending, there are stretching, draw, press, compressions, roll forming. There are bulge forming, pull out process. There are beading technology. Under swaging, there are axial swaging, radial swaging. There are roller swaging process, elastomeric. There are various technologies. There are a few examples. That's an example of a bulge forming. Basically you have applied some internal hydraulic pressure and then localized into the die, put some die in front of it and did some bulge forming. So there's another axial bulge form parts. There's an example of the rotary swage part over here. And the top view, this is the bending of a different tubes, and finally you are joining it by the welding technology. Now let's move to the welding technology. We have few examples of the welding, not that much of welded parts are being used. There are some of the welding technologies are used to during the fabrication process, and after that the welding section is being removed and cut it out to finish the part. The friction assisted welding, as I mentioned earlier, the linear friction, rotary friction, and the friction star welding. There are standard welding processes done by electron beam, laser technology, your TIG process, and MIG welding process. Here is an fundamental showing you the linear friction welding. That one of the example I'm showing you the linear friction welding for attaching that engine blades to the hub. It's a very common technologies these days to do that one. That's a fundamental of the rotary friction welding. As you could see, that it's rotating with a very high speed, and when it is rotating, you are applying some pressure, and then finally joining together under the pressure and the heat generated to bring the metal into the fission stage. Here is a fundamental of the friction stir welding. The tool is spinning with high speed and moving along that path, and because of the spinning, there is a material is under plastic deformation, and joining together when the tool is moving from the left to the right directions. As you could see on this figure B, the friction star is started over here and gradually progressing along the joining length. So here's an example of a friction star weld. So as you could see, this part, there is a friction star weld join in between this part. This part is not a structural part. We can easily apply into the aircraft as some of that container type of applications. Some fuel dams are also being used. Something by this. There is no harm to have a friction star weld join in between. But some of the parts are like this part I'm showing you, that I was involved in this lip skin development many years ago. This is 787 lip skin. We are trying to develop with the titanium, although it was not being used in the aircraft, but still the technology is a valid technology for some future applications. So when we have done that one, we had to prepare the blank before we do the your plastic forming. We had to join a, two sheet blank by the friction stir welding. There are some welding joints in over here, and I think over here there are 4 joints. So the 4 joints will be split into the 4 parts and finally will be fastened together as an engine lip skin. So that's why we are not keeping the friction stir weld into the flyaway part. Actually, we are separating out at the end of the forming process and the manufacturing process. So now I'm moving to the metal cutting and machining technology. As there are, as you could see, some of the machine parts, this is an example of a 15.5 stainless steel flap track part. This is a wing rib from the aluminum forging. There are in a metal cutting operation, there are continuous type of cutting by turning and drilling process, incremental cutting by the conventional milling process. Here is an example showing you of use of a titanium at various locations of the aircraft. As you could see, in a door frame, there are a lot of applications of a titanium. All various different areas. There's an example of a machine landing gear titanium forged part. I mentioned earlier that there are a lot of forging components are being in the landing gear area. Here is an example of the machining components. There are on the wing. There's a huge part we call the channel bend. It goes along the length of the wing, and this is an extruded uh, uh, channel. After machining, looks like that. The initial before machining this is the shape of the extrusions, and after machining that's the shape. How much material we have removed. Many cases we remove like a 30-40% of the material from that whole extrusions. So yeah, I think that's a 30%. Yeah, 30 to 1. The plate hog out extrusion, I'm sorry, 12 to 1%, 12%. Die force 6 to 1, welded 2 to 1 ratio, additive manufacturing 1.2 to 1 ratio. There's another component of the machine, main landing gear beam, die forging initially. There are a lot of monolithic part that we developed and we are using in the aircraft. And the left hand side, you can see that the old configuration is a sheet metal parts are fastened and joined together to make like this. And then we converted in a one hog out machine monolithic part. Then you can minimize a lot of fasteners and joints, and you can, although you are wasting a lot of materials, but in terms of manufacturing is concerned, the cost is concerned, and also the quality in many cases, that many monolithic parts are very very usable, and I should say that more scientific way of using as a aircraft part. Yeah, as I mentioned earlier, that the abrasive, when I was talking about the tribology, that abrasive technology, your frictional technology is how it is being used. So we polish many metal parts, right? And we debar the edge of the part when you sheared off some sheet or plate components. So how we are doing that one? We are using a grinding and polishing operations, right? So this is the fundamental. Your surface finish of this metal part is the before is this, after is this. The surface topography is changing. Basically, it's a plowing process. Abrasive is trying to plow the material from one to other directions. That's the fundamental. So here's an example of this abrasive process by using that belt sanding process to polish that turbine blades. So this is the turbine blade, looks like before polishing and after polishing. So this is a turbine blade formed and machined. There are a lot of machining lines you can see, and after polishing the belt sanding machines, then you can see the nice and good surface finish of the turbine blade. There's another technology is being used, is called that abrasive water jet process. We normally use it to cut a heavy metal. As you could see, is an example of the water jet cutting machines is being used over here. And after we received a big chunk of metal plate, titanium plate from a supplier, then we are using that abrasive water jet technology, and cut it into the geometry of the part before you take it to the next operation of manufacturing processes. before the abrasive water jet was developed, you had to use it either by saw or by your regular machining process to cut out the whole areas. It's very time consuming processes and very expensive to do that one. Let's move to the chemical metal removal process. Chemical metal removal process, we use a lot of chemical milling process, chemical cleaning, but we are stopping it, the chemical milling process. Boeing has stopped internally the whole chemical milling process. When I joined 25 years ago, I have seen a lot of chemical process was done internally. uh, I should mention that we manufacture all the parts not only within the Boeing company, but we had a thousands of suppliers all over the world. They are making it for us actually, and all are being qualified by our qualified subject matter experts. They are qualifying the parts before they accept the parts for the aircraft. So all those technologies, I talked about, all the supplier has the technologies. They are making the parts for us. So since the environmentally is not good to use that chemical milling process, Boeing has, for the safety reason, has stopped internally, but some other outside countries suppliers, they still use it. Uh, Uh, for the chemical milling, we use basically, I'll show you some example next. What's the application of the chemical milling? After machining and forming the part has to go through a lot of cleaning processes because of the darts and oils and other things are being used on the surface. Then it goes to cleaning, then conversion coating. We call the iodine or anodized to make it a environmentally protected surface before it is being painted. There are a lot of hard metal coatings are also being deposited on the steel and titanium surface. Uh, and also those steel and titanium surface also go through some chemical cleaning processes. Here's an example I'm showing you. That's a fundamental of the chemical milling process. Your uh, aluminum foam part is dipped into the tank. It's a heated tank with the chemicals, and there are there are masking area will not be reacted by the chemicals. Only the unmasked area will be, that we call the pocket. This is a panel of a fuselage skin. As you could see on the bluish surface, those are those are being masked, and the remaining area is being chemically removed. So those are that weight reduction pockets and the areas, because we don't need that much of material. So that's why we are removing it. Instead of removing it by the conventional machining, we are removing it by the chemical milling process. But these days, for your information, that lot of machines have been developed mainly in Japan, also in Europe. The panels are being taken to the machines, and actually, the same operations is being performed into that machining operations. So environmentally nice and green process to do that one. So now moving to I'll talk about a little bit about the composite materials. As you could see on this schematic representation, where are the composite materials are going. This is a metal aircraft, is a structure of a 777 aircraft, where the various areas are, composites are being used on this aircraft. I think that 777 has 12 to 14% application of composite materials, as I mentioned on the pie chart before. Major manufacturing technology is a pre-peg layup, is a hand or machine layup. There are in the machine layup, the filament winding process, tape lamination, fiber placement, drape forming. The liquid composite molding is a resin transfer molding, resin film infusion process, and pultrusion process. Here are a few examples I'm showing you that automated tape lamination process. Here is a 787 large horizontal automated fiber placement process for making the fuselage barrel single piece. Here you can see the nose of the front section of a 787 composite fuselage structure. So I'm moving to the measurement and inspection methods. So when you do any manufacturing, either a small part or a large part, your measurement and inspection is a very, very critical things in the manufacturing, because all the parts are very precision, very high tolerance parts, because all the parts to be fitted and joined into the aircraft, because millions of parts in the whole aircraft, and thousands of manufacturing companies are doing it. The parts are coming to the assembly line. The parts has to be dead accurate to assemble the parts. So that's why the inspection and measurements are very, very critical. So the how the measurements are coming into that. So there are many different technologies of the measurements technologies. Your manual type, your computer assisted type, your machine driven like a CMM, your hand driven devices, under the CMM. I'm sorry, that under the manual bench, we are using the measurement tools, the standard functional gauges, functional check fixture. On the computer assisted, we are using a CMM process. We are also using hand driven or guided technology, non-guided technology. There are some other testing and inspection which are destructive type of testing. There are some of the non-destructive type of testings. So those are standard manual precision measurement tools, and the students are using in the lab also in the institute. There are some standard gauges. We call the check fixture. Those are made a separate fixture pre-built, and after forming the parts are taken onto the top of the check fixture to check the gap between the fixture and make sure the parts are formed to the actual contour. Those are showing you the computer assisted technology, the CMM machines. The figure B is showing you the hand driven guided metrology system. There's the bottom one is the figure C is showing you the non-guided laser tracker system. We use a lot of laser tracker system to inspect that the wing skin part, wing spar cords, and many very large parts are very good to use that non-guided laser tracker technology. Let's talk about a little bit about the research and development. What are the major elements for aircraft design and manufacturing? When you are when you are planning to manufacture some part, that you are first checking that what are the needs for the airline customers. Then you are coming to the aircraft design configurations. then how many passengers, capacity, flying range, fuel efficiency. Then is coming to the engineering design side. What are the need for the engineering design? To fulfill the need of the engineering design, you need to have a dedicated research and development to develop the materials, develop the manufacturing technology. You need to have a research and development to do that one. Then finally, all those research and development is coming into that aircraft manufacturing, the cost and performance, and finally the quality and safety of the aircraft. That's the main goal, the quality and safety. That's the ultimate. So here's the R&D model that I developed for a material development. When you are doing some material development, you need to involve with the research and development. So you are introducing a new material. So when you are introducing a new material, then you are considering that what's the cost of the material would be. What's the material properties and applications would be. Can the material be produced to the shape and the form the part? So and how would be the producibility? What's the rate of production would be? How would be the cost of manufacturing? Is it too expensive? And the meets all the cost and performance considerations and before it goes for the final implementations. Because we do a lot of research, but it doesn't mean that all will be implemented. Sometimes many of the research work are being kept in the shelf, that I remember my old days. I developed one of the technology, that electromagnetic forming technology, and formed in a T3 conditions, and finally heated it to T81. And that technology was kept into that Boeing library system for a while. And after 3 years, the engineering department called me, Pradip, I need your help we are going to implement this technology to the aircraft. So that's the way that research and technology works. Many works are done, and so, and time to time, the technology is being used into the aircraft. This is my manufacturing R&D model. So you have the input material that we talked about. We come up with the input material. Now we're moving to the manufacturing technology development, exploring different technology, automation coming into that based on the part geometry that you need to make, improving the existing technology because some of the existing technologies are still there. We do a lot of improvement work. We do a primary manufacturing development, some improving the existing development, that is also part of the research and development, applying the automations into the existing technology. And finally, the goal is we do a lot of lean process, how we can minimize the number of steps between the manufacturing processes and to improve that production rate. And finally, the part cost and the part quality. Now let's show you some slides on automations and innovations in manufacturing. On this figure, we call the 777 fuselage flex track. We use it for automated drilling and fasteners on when you are making that, joining that fuselage skin to making the fuselage structure. There's an example of using the robots. You can see the series of robots are used when we talked about the heat shield and the superplastic foam. On that same particular shop, when they are assembling that heat shield, they are using that robots to make the holes and use the fasteners to do that one. This is then another automations, robotic technology being used for 787 after fuselage, the tail part of the fuselage sections. So basically that many automations are developed and being used. There are many external companies are coming up as a partner of ours, and they are coming up with a different automation technology, and we are using their technology to make our part more competitive and high quality and safe for the aircraft. Um, there, as I mentioned, that additive technology is a very hot technology in the industry at this moment. But additive technologies has some limitations for using as a structural part. There are very small size structural parts are being used gradually day by day. There are a few examples I'm showing the additive manufacturing technology, but there are a lot of applications that we are using as a tooling side. We make the tools using the additive manufacturing technology. It's the tool could be a plastic or some composite materials. There are some metal parts are also tried out. As you could see, that some polymers, some examples. There are since 2002, more than 50,000 flyaway parts are being made by the additive manufacturing technology. Mostly those are non-structural parts. There are few additive manufacturing technologies are being used, wire feed deposition, powder feed deposition.
Timeout.
I'm sorry?
May run into WebEx timeout.
Oh, okay. So how many more minutes I have?
I think in a couple of minutes possible.
Okay, I think it's done. Very good. Thank you.
I think yes.
Yeah, those are the technologies that are being used. Yeah, so what are the future need for technologies? You need to have the advanced aluminum, advanced titanium technology. There are a lot of corrosion resistant steels are coming in, and computational alloy designs and concepts are coming in the manufacturing technologies. There are many technologies development under our process. Your physics-based machining technology, advanced joining technology, flow forming technology, advanced rod and cast powder products, and revolutionary process, your alloy direct manufacturing, innovative hybrid structures. Here are that's a NASA Boeing environmentally responsible aviation model shown over in this one. That's the future aviation blended wing. You have non-circular pressure vessel, advanced composite materials, automated flight, pilotless aircraft, increased monolithic structure, increased additive manufacturing process, increased robotics and time reduction process. Here's a summary, as you can read that one, and I covered most of the stuffs, and sorry for taking a little extra time. I think, yeah, thank you for your kind attention, and I can take some questions and answers.
Thank you, Dr. Saha. Am I audible? Thank you, Dr. Saha, for nice presentation covering all aspects of aircraft manufacturing, considering the material development using the advanced materials, also the basic and fundamental manufacturing processes covering forging, rolling, extrusions, even conventional and non-conventional manufacturing, additive manufacturing, also joining processes such as welding, friction stir welding, etc. Also super finishing operations. As an alumni, I feel proud to say Dr. Pradip Saha, our Pradip Da, for his research work for the development of aircraft component through innovative research work and working such a prestigious organizations like Boeing, which is our dream. Dr. Saha, I have two questions. Am I audible?
Sure.
Yeah.
Can you hear me?
Uh, we know from our childhood that aluminum is basically used for aircraft component for lightweight materials. And so volume to weight ratio, reduction of volume to weight ratio is prime important, I think. And today we have that nano composite materials, carbon nanotubes. Can you light up on that application in aircraft component?
Yeah, so the nano, like I'm not a really composite guy working for Boeing. I know composite technology. I did it on my PhD program, some coursework. There are so we don't use that much of nanotubes. We use a carbon fiber. As I mentioned, I have seen that some of that the skin panels that automated layup process for fuselage and the wing skin. Mostly that we use the carbon fiber technology for making the parts actually. But I'm not sure. Maybe some application of nanotubes in some of the small parts. I'm not sure about it. But like the aluminum to the why we come up with the 50% composite technology in the 787 because of the weight reduction, and the fuel efficiency. That's the main goal. The weight to, buy to fly ratio actually, So to do that one in an aluminum aircraft, so aluminum is lighter, definitely, but the composite is much lighter, right? So I'm not sure am I trying to give you the right answer to that point, your point, or you can ask me another questions to.
Another question, sir. During our flying inside the aircraft, we have observed sometimes air is choked due to huge sound we feel. And have you any thought to reduce the sound level inside the aircraft?
Oh yeah. I'm not sure that when Gautam Sengupta talked about, has he talked about any, because he's one of the area he worked in this area. Um, there are reduction of uh, if you compare that to that old model to our recent model, like your 787, inside is much quieter than the previous models. Even you'll see the next airplane is coming called the 777-89. You'll be flying maybe within the next couple of years by Emirates very soon, or Qatar Airways. There are custom Lufthansa also. So you will see that one, that will be a lot of noise reductions on the aircraft. And also we are trying to do the noise reductions on the engine side also, and the noise is coming not only from the engine, but also that your interaction between the wind and that aircraft structure outside surface, So we are trying to make it a more, what I should say, your aerodynamic to reduce that noises actually.
Okay, sir. Now it is open for discussion.
Sure.
Can I say something, sir?
Yes.
Dr. Saha, thank you for
Sure.
this nice presentation. But I wish there are more photographs than writings, and that way to make it interesting. Anyway, I have got two questions, sir. One
Uh-huh.
is, see, when a plane is used up, it has been consumed, it has finished its life, flying life. But so
Mhm.
much of costly material is there. What do you do? There is a second question. What do you do with it? It's so costly material is there. One. And second is, when you compare a passenger kilometer in a train and a passenger kilometer in a plane, it is 20 times carbon dioxide producing the passenger kilometer in a plane. What is your research approach to mitigate this problem? Thank you. That's all.
Okay. So, so on your first question, that when that plane is the life of the plane is gone, that's a responsibility of the airlines to sell it to a somebody, like you're recycling the material. The airplane is broken into multiple pieces and recycle the material like an aluminum or different materials, and is going to different houses for different purposes like a remelting and using it. So basically is a what I should say, recycling process, and try to save the material again, for not only for the aerospace applications, because aerospace applications raw material is coming as the highest quality raw material. You cannot use too much of scrap on those materials, but is being used for other applications, industrial applications. And the coming to your second questions to that carbon reductions. So I actually, can you repeat the carbon reduction question one more time?
Sir, actually, a passenger kilometer in a train on the surface produces some carbon dioxide, and a passenger kilometer in a plane on the air, it produces 20 times that much of carbon dioxide. So this is a worrying thing for
Oh
research.
yes. Okay. So what is happening these days? There are a lot of research is going on using the biofuel. So Boeing is conducting a series of research, with the many different airlines, and to reduce the carbon footprint, and to increasing the amount of the biofuel to reduce the emissions of the carbon emissions. So it's gradual going on. It is not a matter of 1 year. It will take a while, but it's going on, and is very successful so far. That I could say.
Thank you.
Thank you, sir.
Any questions from the faculty members and from the student side?
If I may mention one point here, I mean, on the line with Achyuda's query, primarily he is talking about the carbon footprint for comparative carbon footprint for air travel as well as vis-a-vis surface travel, fruit train. In fact, there is a movement going on. The movement, they are saying no fly, or no fly for short distances. So no fly movement, they call it. I mean, trying to, it's on the management side, to minimize the air travel for short distances and only take up air travel when it's necessary, absolutely necessary. I don't know, I mean, several aspects people are looking at. One, as you mentioned, the biofuel aspect, still to come that way. It's a long way to go with biofuel, obviously. Some are also trying electrical routes. So, I mean, the question is obviously difficult, and it's difficult to compare also when we attempt comparing air travel and rail travel. One is highly mass transport, concentrated mass transport, other one is not really like that. So anyway,
Also, and also answer to that question, that we are trying to develop that, that what's the 787 to the old aircraft, and also the 777X coming up. So that is a more fuel efficient. So what does it mean though? When you are saving the fuel, either is a bio or a bio combined fuel, you are
Footprint
reducing
also
the
is
amount
getting
of
reduced.
fuel consumption. So that is also reducing the carbon footprint too.
But to your understanding, is there any further scope of increasing efficiency on the engine front?
Oh yeah, always. It is a continuous development going
That's
on.
true, but I mean, the window is quite wide, or because almost
On that that's a very good point on the 777X engine that is coming up. It is more efficient than the 787 because of the very extended lip is aerodynamic,
aerodynamic.
and we are reducing the drag, means you are reducing that amount of fuel consumption per kilometer, so that's the way we are controlling it.
Thank you.
Sure.
Yeah.
Thank you, sir.
Any more questions?
Pavanga
I
might
have
be having queries. Yes.
Amal sir?
It's okay. Thank you, Dr. Shah. It was a very interesting presentation. And start to finish, you really started from very early on manufacturing technology to the latest one. And before I ask my question or other comment, I will definitely re-emphasize both the questions raised by Achyuta. They're very, very relevant because I think any design, it's not our aircraft, any design nowadays, what we do should include a part, what we call design for sustainability. The question is that, or we can also call it design after retirement. The question is that whatever you design, it has a life. What happens after that life? A designer must look into that, must consider that how we can make the best use of it and go from there. But that is, and again, Dr. Shah, you are right, it's an ongoing process. Okay. Now, my comment or question is that you told that there are about 50,000 parts from 2002 to 2022 or so using additive manufacturing. Okay. That is also about, in my simple math says it is about 2,500 parts per year on average. Given the number of parts, millions, that is less than 1% of the total parts developed using additive manufacturing. Here's my question. I'm a big fan of additive manufacturing. And by the way, I work in the University of Texas, Rio Grande Valley. Okay. My question to you is that what is the real trend that the number of parts used in Boeing is 1% or less in terms of additive manufacturing, or the data is going to change very significantly within the next 5 years? And then I have a follow-up question.
Okay, so the Boeing has a dedicated research going on. In fact, I visited a our one of the additive manufacturing shop 2 weeks ago. I was invited to go there to talk with them, and there are so many technologies. I mentioned about the powder feed or wear feed, different things, so it's a continuous process, and Boeing is trying to develop more and more so that we can minimize a lot of machining operations. We can save the monies, and also that at the same time, the design and manufacturing working together to see that what are the best number of parts, even going to a structural parts, or a semi-structured parts order. This is a pretty long path to go forward to increase the volume. But to answer to your question, is moving up actually. Is gradually increasing the quantity uh, of developing and implementing the parts in the aircraft. Yes.
Are you directly involved in with such efforts on additive manufacturing?
I'm not involved directly to the additive manufacturing, but since I'm a Boeing technical fellow, so many things comes to me to get my advice or something for anything, you know. So that much I can say, yeah.
Then,
But I didn't work directly to the additive manufacturing side actually, yeah.
I thought so, just to make sure. But then I'm just asking, say, the answer could be either way. You say yes or no, I don't mind. Are you familiar with so-called hybrid additive manufacturing?
Hybrid additive. So you mean that
Basically, hybrid additive manufacturing means it is mostly for the students. You guys should know it. Means additive manufacturing is augmented using conventional manufacturing, so that you can get a finished part from start to finish. Okay, as an example, we are working on a process where additive manufacturing, as we build it layer by layer, we are adding short pinning method to change the structural property of the part. Okay, there are different methods of doing it. This is one of the example. This is called hybrid additive manufacturing, where you combine conventional and additive manufacturing together. Okay, so here there's coming back to you, Dr. Shah. Are you familiar with it, or you know anything about it, or anything going on?
no, uh, n- no, Mr. Sarkar, I'm not that familiar with that one. So
That's
yeah.
fine. That's fine. Understood. No problem. Thank you. But it was really a very wonderful presentation.
Oh, thank you.
I will have to say some of the slides I really loved it, like development of material, development of manufacturing process. You developed wonderful 2 slides. I loved it. I may use it for my students.
Yeah, you know, like I'm reaching 70 years now, you know, and I'm still working, you know, and busy and enjoying working with the people, you know. So
70, you're just warming up, man. I'm, I'm 75.
oh,
What
you're
is there?
75. I'm so glad to see you. Then I can go up to 75.
Oh, easy, easy. I'm looking to Achyuta. Okay,
Oh,
so he's still active. He's still living and kicking.
61
Very
batch.
glad to hear that.
Youth of 61 pass out.
Yes.
Oh, goodness. Oh.
No,
Well,
he's very active. Thanks, Achyuta.
well, I
We
think
love.
we had a long session, and Suhas, please give me this opportunity of
Yeah, I hand over to Professor Sudeep Ghosh.
so on
for
behalf of the
execution.
department and on behalf of the Centenary Celebration Committee, we must thank Dr. Pradip Saha for this wonderful lecture on this Centenary Lecture series. This is the 41st lecture. We will have one last lecture next week and we have to close it down. We have been running it for almost a year now, starting in December. We have to close it now next week because the exams, as you can see, now see the counts, audience count there. The students have all gone out. So this is the situation. The next week exam will start. So Dr. Shah, thank you very much for joining us. And I could find a lot of information into presentation. Many of the terms, for example, you mentioned something physics-based manufacturing, physics-based machining or something like that. So, I mean, if we could have time, we could ask to elaborate on those things also. But obviously, we will try to get to some time later also for the benefit of students. If we could learn something more from speakers like you, that would be wonderful opportunity, particularly for our students and for members of faculty also. Thank you very much. Here we have this a copy of this certificate, the soft copy of which will be going via email to you. We will also have hard copy along with the memento that we will hand over somehow. We could send a few mementos to US via one of our alumni members who came recently. But a lot of mementos are also lying with us. So we are arranging somehow. We have to send them. If you have some local contacts in or around Kolkata, that will be very fine. We could make home delivery. So
Sure.
that's what we'll be looking for. I will also send common mails to our old speakers also. There are earlier speakers also who are still to receive this thing. So thank you very much. I must also take this opportunity to thank Professor
Yeah.
Mondo for chairing the session, leading the session nicely. Thank you. And the
Yeah,
members
thank
of
you.
alumni.
Thank you from
Kamala,
my
thank you very
side.
much.
Yeah. Yeah. Thank you so much to all of you for giving me that opportunity to talk to you all. And I'm so proud to be an ex-student of B College. And you professors are the main part of our career development. You know, that the fundamental that I learned from B College, I still use it every day of my working life. I
Thank you for
cannot
this
forget.
wonderful
So,
words.
yeah, I'm proud of Shibpur B College.